So in this lecture, we are going to talk about time series data. We will be focusing on the data quality, pre-processing of the data, and some issues with the data before we jump into the time series plots. Okay, here we go. So data quality is important. Time series data sets usually short. Sometimes there are just a few hundred of observations. That means each data point carries a lot of weight when you determine the trends or seasonality and forecasts. If even a small portion of the data is wrong, like measurement errors, missing values, typos, some corruption in the data, this can distort the forecast significantly. And sometimes you have multiple sources of data. The same variable like sales or rainfall or maybe temperature is collected by different departments or different organizations. So the data might differ in quality. So the best practice in this case that we compare across the sources and choose the most reliable one, or maybe combine them if this will improve the accuracy. Also, we have to make sure that data collection is not a one-time job in forecasting. So since you will keep forecasting into the future, you still need a process to keep collecting or gathering new data. That means that the data source you choose must be kind of reliable or sustainable in the long term. Also, for the evaluation, forecast accuracy is always judged by comparing forecasts to actual observed data or values. So if you will compare your forecasts against one specific data set, then that data set must also be the main one used for the training and forecasting. Otherwise, your evaluation will be misleading. And we will be talking about the evaluation criteria in the next chapter. For example, suppose that you forecast daily temperatures and you have data from 3 different weather stations. So if your goal is to evaluate forecasts against station A's data, then station A should be your main training source, not station B or C. Otherwise, even a good model may look bad just because the comparison was inconsistent. So, the overall idea in this slide that the data quality is important because data sets are small and some errors can distort the results. So make sure that you have a reliable source of data. And as we know as a data analyst that we spend a lot of time just cleaning our data. Temporal frequency, data can be very frequent. So like in stock trade, for example, data are collected every minute or every millisecond. In the store sales, maybe every purchase is recorded immediately. So the raw data is very high frequency in this case. But high frequency doesn't always mean that we are going to have a better forecasting. Just because the data exists minute by minute doesn't mean that the right level to use forecast or this is the right level to use for the forecast. Because high frequency data usually contains a lot of noise, which is a short-term random fluctuations. Like in grocery store sales, minute by minute look very peak, like during the lunch maybe and quiet at night. So if your goal is to forecast next day's sales, all this minute by minute noise isn't useful. So in this case, you have to make sure that we have to watch for this. So what to do? We have some solutions actually. To solve this issue, sometimes we aggregate to cursory frequency. Like minute, we change. We collect all of the minutes to an hour. We change it to hour, or maybe hours to day, or day to week. So we have longer intervals by summing or averaging, aggregating the data. So aggregation smooths out the random or the noise. So underlying patterns like trend, seasonality can be clearer. And as I said, instead of a minute level grocery sales, use daily totals. just easier to forecast tomorrow's sales simply without having a minute or hour. Even when high frequency forecasts are required, sometimes forecasts are needed at high frequency. Still, it can be easier to do many things. First, aggregate to the lower level of a frequency. We build simpler or more stable forecasting model, then disaggregate back to daily using interpolation or other rules. Maybe an example about this: if your goal is to forecast daily ATM cash withdrawals, maybe you can think about aggregate the data from daily to weekly, then forecast the weekly withdrawals. Then we use interpolation, some numerical methods, to spread the weekly forecast back into daily values. So this is the overall idea that just we have to be aware about the data. If it's collected minute by minute, or we need to smooth it, we have to think about whether you keep it or use daily or weekly totals. Series granularity, and this is an important concept, which is the coverage or scope of the data. So what does the data cover actually? So what subset of the real world your series is measuring? What kind of dimensions are you covering? Like geography, national level versus state level. If we just talk about the Amtrak example, the population, are you covering all passengers or just the senior citizens or just the students? So, or the time of the operation, are you thinking about all day or just rush hour or weekends only? So all of these examples just tell you exactly how or what is the scope of the data, what is your goal actually. And there are kind of a trade-off if you choose to have a fine granularity versus coarser. Fine granularity, that means we have a very detailed set of data or very detailed data sets. This is more specific to your exact question or goal. But the problem with this, we have smaller counts, so we have high variability, and we may have many zeros. Like if you think about daily senior citizen riders on a small route, so you're going to have many zeros actually. So because it has a high noise, it's going to be harder to forecast. On the other hand, if you get a coarse granularity, which is more aggregated data, the pros of this that we are going to have more stable patterns because you have larger counts and you're going to have smoother trends. However, it may hide important differences across maybe the routes, the times, or the groups, if we're talking about the Amtrak again. So what are the implications for forecasting? So the chosen granularity level must match your goal. So you have to know the goal. If the goal is the national policy, so national level data makes sense. If your goal is staffing a specific station during rush hour, then you need to fine-grain data. So very fine-grained series requires different methods. So instead of forecasting numerical series, you may need a method for binary data. For example, was there at least one senior citizen today? You say just yes or no. You do not use the count 3, 4, 5, 0 because we are going to have many zeros. So in this case, you change your data to binary. Yes, no, yes, no. So to decide, you have to know your goal first, the forecasting goal. Then you tell exactly what kind of scope of data you are going to use. So why domain expertise matters? Because if you have the best data and the best statistical tools, you still need experts in that field to do many things, to choose the right data, interpret unusual patterns, and judge whether the forecasts are actually useful for the organization or no. So without having domain knowledge, forecasts can be sound but practically useless. So that's why we need a specific person who knows. Where domain expertise comes in different places. Choosing data. So because you have to choose data at the end of the day. Do you want your data daily or hourly or by minutes or whatever? How far back to collect history? Which source is most reliable? Interpreting patterns like seasonal effects. Experts know why sales always spike at year end. You'd have to know the outliers. Larger drop in the production might just mean an annual plant shutdown. Sudden shifts. A new company policy, regulation, or competitor can change the trend permanently. The other thing is explaining events, like after-hour sales only make sense if you saw hours, or no sales day might just mean everyone was out for the company picnic or whatever. Also, evaluating usefulness, forecast accuracy numbers, like using MAPE, SE, we can speak about this later, do not tell you if the forecast is good enough. Domain experts help judge if the forecast supports the organization goals or not, staffing, pricing, budgeting, and so on. Forecasts are not just an academic exercise, they are supposed to support decisions, right? Because again, inventory, pricing, policy, staffing, profiting, sales, etc. So that means you need to close communication with domain experts, especially when forecasts are produced by outside consultants. An example, suppose you are forecasting call volumes in a customer service center. So the model shows a huge drop every December 25th. So without domain knowledge, you might treat it as something not normal, right? With domain expertise, it's a Christmas day. Offices are closed. So immediately, you keep the forecast realistic and aligned with the actual business needs. This is the time series plot. So the time series usually contains of two major parts, okay? The first part, we call it the systematic or the structured or the explainable behavior. That contains the level and the trend and seasonality. The level is not here in this picture. The level sometimes used in some books, and some books they do not, they just merge it with the trend. So the level is the average value of the series. The trend is a long-term upward or downward movement. Seasonality is the repeating short-term patterns. So if you look at the trend here, it's going upward. This is a trend. This is a structure. This is the explainable part. The other explainable part is the seasonal. Look at the seasons. So the seasons, the small ones. So you have a short-term patterns, like these are maybe yearly, right? Or every half a year we have a season, every 6 months, right? So all of these are explainable. There is a cyclical part, but there is something not systematic, which is the irregular fluctuations or the noise. So this noise, we don't know, we cannot predict or we cannot forecast. These are very hard to predict. So that's why in time series, I did not talk about the level. The level is the average, as I said, but it doesn't exist in this picture. So the point is, we're going to speak about this later. The point is, we are going to decompose this time series. We are going to isolate the noise and maybe isolate the seasons because we want to focus on the trend first. Or we're going to focus on the seasonal, maybe. But the idea is we want to isolate this. So there is a kind of techniques that we are going to use to decompose this plot into sub or smaller or different plots, that one that deals with the trend only, the other one deals with the seasonality, and just separating the noise out of this. So one of the techniques that we are going to use, we have something called the additive model. We are going to separate, or we are going to write or decompose the YT into a summation or addition of the 4 components or 3 components. This can be trend plus seasonality plus the noise, or maybe you can separate the level from the trend. So the level could be part of the trend. So trend plus seasonality plus the noise. This is the additive model. And we have a multiplicative model, which is the time series will be decomposed like level times trend times seasonality times noise. So what's the difference between the additive and the multiplicative? In the additive, the seasonal pumps are always the same size, no matter the level. So December adds like 50 units plus 50 units. Whether your base sales are 500 or 1,000, we don't care. So we have the same size of seasonality. However, in the multiplicative model, the seasonal pumps grow or shrink with the level. Like December adds 20% plus 20% every year or every whatever. And additive assumes effects are constant. Multiplicative assumes effects kind of a scale. So we have a scale, but these are constants, right? So why we care about this? Because if we know the systematic part, then we can forecast with confidence actually. So the baseline or the level give you a starting point, the trend tells you the direction, and seasonality tells you to or anticipate the repeats. And if you understand the noise, you can say this is the best guess, but here is how uncertain it is. You can add the prediction interval, and we are going to speak about this later. So we need both of them. We need the systematic part and the unsystematic part. As I said, why do we need to decompose? Why do we need to decompose the time series? Because as I said, only the repeatable part, the systematic part, can help you predict what's going to happen tomorrow. The random bumps cannot. So the random noise, the fluctuations, we have no control over them, right? So if you mix both of them, you will probably chase accidents instead of patterns, right? So these are some reasons that I'm going to go over. Predictability lives in patterns. As we said, weekend spikes, December surges, a steady upward push, those repeats. They are useful insights. However, noise does not repeat, like a snowstorm, one day promo glitch. These are offs. So we have to learn them, or we have to know them. But if you add them to your forecasting, you're going to make wrong forecasts. Separating them prevents overreacting. So if last Tuesday, let's say, dipped because of a power outage, and you treat it like a real pattern, we have an issue because you'll underorder next Tuesday, right? It makes forecasts steadier and more accurate. You anchor on the baseline level, so adjust for direction, which is a trend, and add the regular pumps or wiggles, seasonalities. That beats trying to fit every bump. Also, you can be honest about uncertainty. After you pull out the patterns, so what is left is the noise. So the noise tells you how wide to make your prediction range, the prediction interval, right? And finally, it's going to improve your decision. Staff for the known rush hours, which is a kind of a pattern, do not panic over kind of a quiet day, which is a noise. So it makes your decision or improve your decisions. And these are some common trend and seasonality patterns. If you look at this, we have a constant trend. It's a constant trend. It doesn't go up or down overall. We don't have any seasonal. It's just fluctuating randomly. If you look at this one, also you have a constant trend, but we still have kind of additive seasonality. We have the same behavior repeats every sense, right? It's additive because we are adding the same numbers every time. It's the same thing. Look at the variation, doesn't go up or down. However, this one, we still have a constant trend, but the multiplicative seasonality. So we use a multiplicative decomposing here, because the seasonality is becoming bigger and bigger every time, but the same behavior. So we are adding like 10% every time or 20% every time. Here we are adding just 50 units, 100 units every time. So the same thing. In this time series, we have upward trend, but there is no seasonal because nothing is repeating. We don't have a repeating pattern. This one, we have upward linear trend with additive seasonality, right? This one we have upward linear trend with multiplicative seasonality. It becomes bigger and bigger. We have a rate here. Now we have non-linear trend, which is upward exponential, no seasonal. Upward exponential with additive seasonal. Upward exponential with multiplicative seasonal. This third word polynomial trend, the same thing and the same thing with multiplicative and additive seasonality. And we have many others patterns. Visualization first, because tables are not enough. So we have to see tables. We have to see not tables. We have to see graphs. We have to see plots. A simple plot over time allows you to see patterns, allows you to see trends, seasonality, and the levels. It allows you to see outliers, missing values. So you can look at overall what's happening in your data set. So the first thing to do is actually cleaning your data, but after that you have to do visualization. So you have to see the time series plot. And this is an example of the graph that you see, and we are going to do this in R. The Amtrak ridership. We have the horizontal axis, which is the time. It may represent days, months, and years. Vertical axis represent the measured values, the ridership here. And if you look at the average, the level is about 1,800 riders per month. So these are monthly data. So 1,800 is the level. We have kind of a U-shaped trend, right? Do we have seasonal? We do have a seasonal. It's not very clear. Maybe we have to just stretch it to see it well. We have kind of a patterns repeating here, and these spikes and valleys, right? Sometimes we need to go into to zoom in to see more actually, because sometimes the chart or the series or the plot hides smaller patterns. And an example of Swiss tunnel traffic, we're going to talk about this later in the next slide, that maybe we need to zoom in to see more patterns. What problem we can see from the visualizations? The extreme values, outliers, like sudden spikes, drops that do not fit into the pattern. Other problem is in unequal spacing. Sometimes you have missing time stamps or irregular reporting. This is important. We have to notice about this. We have to look at the why we have unequal spacing, what to do in this case. The other thing is missing data. Sometimes we have flat lines or gaps in the series. So in this case we have to do some solutions. We do have solutions. So in the Swiss tunnel traffic, if you look at this data, we don't see exactly what's happening. However, when we just zoomed in, we just look from here, it's November 2003, November 2005. Here we just look at from February 2004 to May 2004. So we see exactly what we do have seasonality here. It's a clear seasonality. So fewer weeks or days, we can see better data. So in this case, we can focus on a specific data set or a specific range to just uncover these patterns. So as we said, when we do visualizations, sometimes we want to capture the trends. To capture the trends, and I'm going to speak about this maybe in detail later, some techniques that we are doing to capture the trend is changing the scale or adding trend lines or suppressing seasonality to better see that trend, or look at the global versus local patterns. Changing the scale, sometimes instead of plotting raw values, we plot their algorithms. And again, I'm going to talk about this later. Adding trend lines, it's important because sometimes the line is linear, exponential, polynomial. If you add this, it gives you a quick check of the trend type. Seasonality, sometimes when you have a strong seasonal, it could hide the long-term trend. So what you do, you aggregate to coarser time units to smooth these wiggles of the seasonality. Or plot separate seasonal sub-series, and we're going to do this. Or sometimes we are using the moving averages, and again we are going to do all of this. Or you may look at the global versus the local patterns. The global patterns, which is the structure that holds across the whole series, or local pattern, the structure that only holds for part of the series. So sometimes we have to recognize these global versus local patterns to capture the trends. And before we start working in data, we have to do some data processing or pre-processing of the data. Why is that? Because when you do forecasting, we're expecting to have clean data. And in data science or in data analytics, we have to make sure that the data is clean enough to conduct some analysis. The same thing with the forecasting. If you go straight into modeling without fixing missing values, you are having a risk of getting either no forecast at all or maybe very bad forecasts. So we have to detect and handle these missing values before modeling. So different techniques can be used. Some methods cannot tolerate missing values and some methods can handle missing values. Like ARIMA, exponential smoothing, they cannot tolerate missing values. Others they can tolerate and they can handle them, like linear regression. So the question is how to deal with these missing values. We have many options. We have imputing options, fill them up or fill the data in, maybe with the averages or the median or whatever, or ignore them, just to drop them, or unsample them, like combine both. Run one model on imputed data, another model when we have the drop data, then we combine the forecasts. The problem that if we did not detect missing values until maybe later, so the method maybe is not going to work. I mean, you have to redo all of the work. So you have to, at the beginning, to address the missing value thing. So equally spaced versus unequally spaced series. Equally spaced means in any regular time series, each observation is recorded at a fixed intervals, like daily stock price or monthly unemployment or quarterly GDP and so on. Time gaps are always the same here, 1 day or 1 month or 3 months. However, sometimes we have unequally spaced series. So they are coming in an irregular intervals, like they are not evenly spaced. Like what? Bus arrivals. Bus do not always come exactly every 10 minutes. Or maybe online auction bids. Bids can come seconds apart, then nothing for hours, and so on. Holiday sales, Christmas, Easter, irregular dates each year. The problem is, we do have a problem, because why this is a problem? Many forecasting methods like ARIMA and exponential smoothing assume equal spacing, because they directly use yesterday, today, then tomorrow kind of structure. So if the data points are irregular, the structure breaks. So what can be done? So we can use methods to handle irregular spacing directly. Some regression or machine learning methods can use irregular timestamps, which is okay. Or convert to an equally spaced series, interpolation. Fill in the missing values with the regular intervals. And many techniques can be actually done in this case. If you do this, you are keeping consistent and you have a regular spaced data, then you can do forecasting. The other thing is the outliers. Outliers is something, we have a statistical way to calculate the outliers, but sometimes, for example, in a daily sales usually between 400 to 600 units, but one day it shows 2,500. So there's an outlier, clearly outlier. Maybe temperature someday it shows like negative 70. This is an outlier. So sometimes, or the outliers, why this is important, because some methods are very sensitive to extremes or outliers, as we said before. So the question, do we need to remove them? We have many solutions. Sometimes we fix them if they're wrong. Sometimes we remove them. And sometimes we investigate these values if they're correct or no, right? So it depends on the cause. Is it data entry error? Is it unusual one-off event? Is it like a true event that could occur? So you either fix or remove, or if it's unlikely to happen again in the forecast horizon, you might just exclude it. You just remove it. So maybe it's part of the real pattern. You have to keep it because it's a true event, right? If you're uncertain about it, you can generate 2 sets of forecasts. one without the outliers, one with outliers, and C. Choice of a time span. So how far we have to go back? Do we need to use too little data, too much data? Maybe if you use too little data, we have not enough information to capture patterns. But if you use too much data, you risk including periods where the environment maybe was very different, which can be misleading the model. Too much data. If you go back like years and years, maybe that's not good, right? An example, which is a good example about the air travel versus train in India. So before the low-cost airlines, many people used first-class rail. After airlines arrived, first-class rail rider dropped very sharply. After railways cut fares, ridership increased again. So if you include all of the history, the model sees conflicting patterns, growth, then crash, then recovery, right? So only use the segment where the environment matches the future. So because you're looking for the future, so you choose the right data. The trade-off, short versus long history. Short history risk of missing important long-term patterns like seasonality across years. However, long history risk of polluting the model with outdated patterns caused by a different context. So when you prepare your data, you do not just include everything blindly. You just use enough to capture the pattern. This is the bottom line. This is everything in this chapter. We are going to jump into our studio now. Thank you.